For years now, anyone working in AI has heard this same looming anxiety, right? The data dilemma.
Right.
Feels like we've hit a wall. Real-world data is messy, it's so expensive to collect, and worst of all, it's finite.
We're running out.
Exactly. We keep hitting these physical scarcity, privacy laws like GDPR, you name it. But what we're seeing now, it's a massive shift. The future isn't about finding better data, it's about creating it.
Yeah.
Okay, let's unpack this.
And that is really the core idea in the sources we're looking at today. For a long time, people thought synthetic data, artificially generated data, was just a spare tire.
A patch. Something you use when you run out of the real stuff.
Precisely. A patch. But that's not the reality anymore. We're looking at synthetic data as the turbocharger.
The turbocharger. I like that metaphor. It implies, perfection, massive acceleration. But doesn't using artificial data create its own risks? I mean, does that turbocharger add complexity or maybe synthetic flaws that the AI then learns?
That's a fair challenge. It absolutely does add complexity, but the consensus is that the benefits, the control, the abundance, they far outweigh the risks. And those risks are getting smaller and smaller as the tech gets better.
Okay.
What we're really seeing is a fundamental paradigm shift. We're moving AI from an era of observation, which is just learning from what has already happened,
Passively learned.
to an era of imagination, an era where the AI learns actively from what could happen, or even what should happen.
That distinction, observation versus imagination, that's huge. It sounds like we're finally breaking free of the constraints of the physical world.
We are.
So for this deep dive, we're going to explore how this turbocharger is demolishing those old bottlenecks. We'll look at 3 big areas: accessing fields that were previously impossible, achieving this incredible development velocity, and maybe most importantly, proactively engineering fairness into our AI.
Exactly. Let's see how this idea of abundance just changes the whole game.
Let's start with those impossible fields, because this is where you can really see the limits of the real world. Traditional AI can only go where data already exists, right?
Right.
And if that data is too scarce or too sensitive, well, those industries become what the sources call AI deserts.
A great term for it.
And synthetic data is basically the irrigation system. It's what makes those deserts bloom.
And the first barrier it just crushes is what we can call the privacy paradox. Think about finance or healthcare.
Yeah.
They are sitting on mountains of the most valuable data imaginable: transaction logs, patient histories, but they can't use it.
They're legally and ethically blocked.
Completely. Privacy laws, and rightly so, stop a bank from just handing over millions of real transaction records to train some new fraud detection model.
It's the ultimate catch-22. The very data that could save millions or save lives is the data they can't touch.
So the solution they're using, it's this concept called digital twins.
Digital twins.
Yeah. Institutions can generate these comprehensive synthetic profiles of their customers or their patients. And crucially, they don't just mimic stats. They transact, they spend, they show subtle behavioral patterns, exactly like real people.
So they're not just averages. They have the same weird quirks as real customers.
Exactly. The financial irregularities, the market volatility, it's all in there. But every single person is purely fictional. This lets them train these incredibly aggressive AI models on realistic data without exposing a single real client's history.
That's the perfect fix for the sensitivity problem. But that raises a question for me. If it's learning from fictional people, how do we know the twins are actually good enough? How do you audit that to stop the model from learning synthetic flaws?
That's the key step. This isn't just random generation. It's built on the statistical DNA of the real data. It captures the distributions, the correlations, all of it.
So it's a very controlled process.
Highly controlled and highly audited. The main verification step is something called utility testing. They make sure that a model trained only on the synthetic data performs just as well, sometimes even better, when it's tested on a small, protected set of real data.
Ah, okay. So if the model trained on the twins can spot real fraud, then you know the twins are robust.
You got it.
That makes sense. Okay, so let's flip to the other side of the impossible fields problem. Scarcity, where the data just, doesn't exist in large numbers.
Right. You can't build a machine learning model on a few hundred data points. Think about rare diseases. You might only have a few hundred confirmed cases in the whole world of some specific genetic mutation. The real data tells you the disease exists, but you have no variability.
Not enough examples to see all the different ways it can show up.
Exactly. You don't know how it progresses in people with different diets or different backgrounds. It leaves the AI model brittle. It can't handle real-world outliers. You can't stress test a model with data you just don't have.
So what's the mechanism there?
It's advanced simulation. By generating synthetic biological data, simulating thousands of hypothetical patients based on what we know about genetic pathways, the AI can be trained to recognize patterns it has literally never seen in a real person before.
It's pre-learning based on simulated possibilities.
And it's not just medicine. I mean, think about infrastructure. You're developing a new deep-sea turbine for tidal power.
Right.
You can't wait 20 years for every possible stress fracture and material failure to happen in the real world. You simulate them. You generate data on catastrophic scenarios that you hope never, ever happen.
So you're training the AI for the 1-in-1,000-year event that real data might never capture.
That's it. The scarcity barrier is just bypassed. You generate all the complex variations you need on demand.
Okay, so that's breaking past physical and ethical boundaries. Let's talk about the second section. Breaking the speed barrier, what the sources are calling velocity.
This is where things get really dramatic. You have to contrast the old way of doing things with what's possible now.
So what did the old development loop look like?
The old way was agonizingly slow. Let's say you wanted to build an AI for industrial inspection, something to spot tiny defects in solar panels.
Okay.
You were locked into this long, expensive grinding loop that could take months.
Walk us through that old loop. What were the steps?
Okay, so first, you had to wait for things to break. Literally wait for a solar panel to crack. Second, you send someone out, a photographer or a technician, to capture the data. Third, all those images have to be manually labeled by people.
Which is slow and costs a lot of money.
And it's prone to error. And only then, after all that, could you even start training your model. And if the AI failed, you had to start the whole collection process all over again.
It sounds like you're waiting for the world to catch up to what you need to train.
Yeah.
But synthetic data just flips that completely.
Completely.
This shift from months to hours sounds almost unbelievable. So how does this, what do they call it, the data flywheel? How does it actually work?
So instead of waiting for real life, developers now use something called procedural generation. It's a method that uses algorithms to instantly create training data.
Wait, procedural generation?
Yeah.
Like in video games?
Yeah.
The way they build those huge open worlds.
Precisely like in video games. It's the same idea. But here's where it gets really interesting. It's not just randomness, it's controlled randomness.
So you're saying a video game technique is solving high-tech industrial problems?
I am. And it's surprisingly elegant. You define the parameters. So instead of waiting for a cracked panel and evening light, you just tell the system, generate 100,000 images, vary the crack size from tiny to large, add different levels of dust, and change the lighting from bright sun to dusk.
It just spits it all out.
The entire perfectly labeled library of defects. In minutes.
And that's the key, right? The data is perfectly labeled from the moment it's created because the generator made the defect, so it knows exactly where it is.
Absolutely. And that is the core of the data flywheel. Engineers used to be able to iterate on their code really fast, but the data was always this huge, slow bottleneck. Now they can iterate on the data as fast as they iterate on the code.
So if a model fails?
If the model fails to detect, say, hairline cracks in foggy conditions.
A corner case it hasn't seen enough of.
Right. The developers don't wait for a foggy day. They just go back to the generator.
They just dial up the fog setting.
Exactly. They tweak the parameters, tell it to output thousands of new foggy hairline crack examples, and they retrain the model instantly.
Wow.
You can find a vulnerability in your AI and fix the data causing it in a single afternoon. That collapses a timeline from months to hours. That is what unprecedented velocity looks like.
We've covered privacy, time, but I think the most profound application of this has to be in ethics. Actively engineering fairness. Because real-world data is really just a mirror of history and history. Well, it's full of bias. If you just collect data from the world as it is, you're just reflecting what was, not what should be.
That historical bias is maybe the single biggest ethical challenge AI has ever faced. And AI is just a pattern recognition engine. If the data has biased patterns, the AI will learn them, and it will perpetuate them.
The classic example being the hiring AI.
The classic example. You train a system on 20 years of resumes from a field where men held 90% of the engineering jobs. Well, the AI is going to learn to heavily favor male candidates for those jobs.
And it's not because the algorithm is sexist.
Not at all. It's because the training history is sexist. And you can't just remove the gender markers from the real data. The AI is smart. It finds proxies. It finds other clues in the resume.
So we can't just hope the AI ignores the bias. We have to actively intervene.
We have to. And this is where synthetic data provides this really proactive solution through something the sources call counterfactual generation.
Counterfactual generation.
Yeah.
So creating a version of reality that didn't happen.
This is where data creation becomes an active, positive act of ethical engineering. We're not just accepting the mirror of history anymore. We are deliberately shaping a corrected reality for the AI to learn from.
Okay, so how does that work in practice? How do you use a counterfactual, a hypothetical, to mathematically balance the scales?
Well, the first step is you have to identify the bias. So if historically only 10% of engineers hired were women, that 90-10 ratio is baked into your real data.
Right, that's your baseline.
That's your biased baseline. Counterfactual generation lets you define a fairer ratio, let's say 50-50. And then you deliberately generate hundreds of thousands of synthetic profiles of the underrepresented group.
So female engineers in this case.
Female engineers, minority executives, you name it. And these profiles mirror the exact skills and experience of the high-performing majority profiles. You're creating the data that should have existed if history had been fair.
That's powerful.
It is, because you don't throw out the real data. You just inject these balanced synthetic examples into the mix. You statistically offset or dilute the historical bias. You flood the system with enough corrected reality that the model learns the 50-50 ratio you engineered.
Instead of the 90-10 ratio that history gave us.
Exactly. It turns data design into this powerful lever for social and economic correction.
That feels like a fundamental shift in thinking. You're not just filtering out the bad history. You're drowning it out with a statistically sound, corrected future. That gives us a tool to build AI that's explicitly fairer than the flawed world it came from.
It lets us train models that reflect the society we want to build, not just the one that existed 20 years ago.
So what does this all mean? We've covered a huge amount of ground here. We've seen how synthetic data is this turbocharger for AI. We broke the constraints of privacy in impossible fields. We achieved incredible velocity with the data flywheel. And we gained the power to actively engineer fairness by offsetting historical bias.
It means we're crossing a threshold. We're entering the age of data abundance. Data is no longer this finite commodity that's expensive and slow to collect.
It's a renewable resource.
A renewable resource. Controllable, tailored to our exact needs. By decoupling AI progress from the limits of the physical world, the cost, the scarcity, the bias, we can build systems that are more private, more adaptable, and ultimately fairer than the real world they learn from. The constraint is broken.
The data bottleneck is gone. The turbocharger is fully engaged.
And that raises an important final question for you, the listener, to think about. If the technical bottleneck of data is now gone, if we can simulate any scenario we want, both good and bad, the only limit left isn't what can be simulated, it's what we choose to simulate, and why. Now that we have the power to engineer our future reality through data, what principles, ethical, legal design principles, will guide that choice?